We have a linear model from last episode. It takes an input and outputs a guess, but we still haven't said what it means to be good at guessing. If we don't define good, there's nothing to improve. Today is about inventing that definition from scratch, a loss function, a single number that measures how wrong our model is. Imagine we have a data set, inputs x and observed outputs y. Our model predicts y hat equals mx plus b. For each data point, there's an error, predicted minus observed. The key move is to turn all those signed errors into one score. That score should be 0 only when predictions match observations, and bigger when predictions are worse. Why not just add the errors? Because positive and negative errors cancel. A model that is wildly wrong half the time could still sum to 0. So our loss must ignore the sign, or at least punish both directions equally. That's the first principle, symmetry. If being too high is just as bad as being too low, the loss should treat them the same. Two obvious ways to remove the sign are absolute value and squaring. Absolute error grows linearly. Twice the error means twice the penalty. Squared error grows faster. Twice the error means 4 times the penalty. So squaring aggressively punishes big mistakes. That might be good if big mistakes are especially costly, or if we want the math to be smooth for later optimization. Now we need to combine penalties across all data points. The simplest is an average. For squared error, that gives mean squared error, 1 over n times the sum of squared errors. Often we include a 1/2 factor too, not for meaning, but because it cancels a 2 when we take derivatives later. The loss is a function of parameters m and b. There's a geometric meaning hiding here. For a fixed m and b, each point has a vertical residual, the distance from the data point to the line, measured straight up and down. Squared loss is literally summing the squares of those vertical distances. So training becomes slide and tilt the line to make the cloud of vertical gaps as small as possible, but with big gaps punished extra hard. So why is squared error such a common default? One reason is smoothness. The squared penalty has a clean slope everywhere, including at 0. Absolute value has a sharp corner at 0, which makes the idea of a single best direction to improve a little more subtle. We're about to invent gradient descent, and smoothness will make that invention feel inevitable. Another reason comes from a story about noise. Suppose the true relationship is a line, but every measurement of y is nudged by random noise. If that noise is Gaussian, then the most reasonable parameters are the ones that make the observed data most likely. When you write that likelihood down and simplify, maximizing it becomes exactly the same as minimizing the sum of squared errors. But squared error is not the only honest loss. If you care about being robust to outliers, absolute loss can be better because it doesn't explode for a few bad points. And if the output is not a number but a yes or no label, squared error is awkward. Then you want a loss that matches probabilities. The loss is not a law of nature. It encodes what mistakes matter. Now comes the key bridge to the next episode. Once you pick a loss, training means searching for parameters that minimize it. For our line, the loss depends on 2 numbers, m and b. So you can imagine a landscape over a plane. Every point in parameter space has a height equal to the loss. Learning is just finding the low point of that landscape. We've invented the missing piece, a loss function, a rigorous way to say what it means to be wrong. For linear regression, mean squared error is both geometrically clear and mathematically convenient, and it even drops out of a simple noise story. Next episode, we'll invent the engine that walks downhill on that loss landscape, gradient descent.